The recent behavior and orbital path of the interstellar object 3I/Atlas has drawn significant attention within the astronomical community because of the remarkable sequence of coincidences that occurred as it passed through the inner solar system. Three particularly striking facts stand out when examining its trajectory. First, 3I/Atlas reached its closest approach to the Sun on October 29, 2025, an event known as perihelion. Second, this perihelion occurred only 8 days after the object had reached solar conjunction relative to Earth on October 21st, meaning that Earth, the Sun, and 3I/Atlas were briefly aligned in a straight or nearly straight line, with the Sun positioned between Earth and the object. Third, just 26 days prior to perihelion, on October 3rd, 2025, 3I/Atlas crossed the ecliptic plane, the imaginary plane in which most of the planets orbit, at a moment when it was also closest to Mars. Such a compact cluster of orbital events occurring in such close temporal proximity is unusual enough that it has prompted discussions about whether this apparent alignment of circumstances is a purely random coincidence, or whether it may reveal some deeper structure or pattern in the object's origin or trajectory. Regardless of whether one interprets these alignments as mere happenstance or as something potentially pointing to design, these events nevertheless created an extraordinary scientific opportunity: the ability to observe, in real time, the effects of gravitational lensing of the object by the Sun as its light passed extremely close to the solar limb. According to the framework of general relativity developed by Albert Einstein, the gravitational field of a massive object like the Sun warps the fabric of spacetime, causing the path of light traveling near it to bend. This bending is not a hypothetical idea, but a measurable physical effect that has been confirmed repeatedly since the early 20th century, beginning with the famous 1919 solar eclipse expeditions. The mathematical expression for the angle by which light from a distant source is deflected by a massive body like the Sun involves several factors: Newton's gravitational constant g, the mass of the Sun m, the speed of light c, and a set of distance parameters that describe the relative positions of the source, the deflector, and the observer. Specifically, the deflection angle is given by the expression 4gm/c superscript 2 times d underscore slash a times d underscore s times d for d, where d underscore d is the distance from Earth to the Sun, the deflector. D underscore s is the distance from Earth to the source, in this case, 3I/Atlas. D underscore ds is the distance from the Sun to the object, and A is the angular separation between the apparent image of 3I/Atlas and the center of the Sun. When the values at perihelion are substituted, D underscore d equals 1 astronomical unit, D underscore ds equals 1.36 astronomical units, and D underscore s equals 2.36 astronomical units. The resulting deflection angle amounts to approximately 0.27 arcseconds divided by the angular separation expressed in degrees, or more explicitly, 0.27 arcseconds/a/1 degree. This value is small, but well within the detection capabilities of high-precision astronomical instruments, especially modern telescopes equipped with sensitive detectors. The timing of this effect could not have been more advantageous. Because 3I/Atlas passed so close to the Sun in late October 2025, astronomers gained a rare window during which the deflection of its light by the Sun could be measured and compared to its predicted deflection within general relativity. Detecting such a small effect might seem challenging, but observatories with exceptionally high resolution, such as the Atacama Large Millimeter Array ALMA, are equipped to register positional deviations on the scale of tenths of arcseconds. Indeed, on October 29, 2025, the very day of perihelion, ALMA reported that 3I/Atlas exhibited a non-gravitational acceleration. The object appeared roughly 4 arcseconds away in right ascension from its expected position based on its projected orbit. While the gravitational lensing by the Sun contributes only a fraction of that reported deviation, the presence of such a discrepancy has generated substantial excitement. It suggests that within the overall measurement, there may be a subtle, embedded signal from the solar gravitational lensing effect. A detailed reanalysis of the ALMA data could potentially reveal this faint imprint, allowing astronomers to isolate the relativistic lensing contribution from the larger anomaly, and thereby test general relativity under conditions involving an interstellar visitor, a scientific opportunity that arises extremely rarely. The story does not end with gravitational lensing or orbital deviations. Additional observations near perihelion were made using several solar monitoring spacecraft, including NASA's STEREO mission, the Solar and Heliospheric Observatory, SOHO, and the GOES 19 satellite. These instruments routinely monitor the Sun and its surroundings, which means they were well positioned to capture data as 3I/Atlas passed close to the solar disk. What they recorded was extraordinary. The object displayed an unprecedented brightening near perihelion, becoming significantly more luminous than predicted from standard cometary behavior. Not only did its brightness increase sharply, but its observed color shifted toward a shade that appeared bluer than the Sun itself. This is highly unusual because most comet-like bodies brighten due to sublimation of volatile materials or dust scattering, processes that typically produce a color signature different from what was observed in this case. The combination of intense brightening and abnormal coloration suggests that 3I/Atlas might possess unusual physical properties or contain materials that do not behave like those of typical comets or asteroids within our solar system. When combined with other previously noted peculiarities, these observations raise the total number of anomalies associated with 3I/Atlas to 9. Taken together, all these features paint a picture of an object that is far from ordinary. The close temporal alignment of major orbital milestones, conjunction, ecliptic crossing, and perihelion, might be coincidental, yet the clustering is striking enough to merit attention. In scientific disciplines, especially astrophysics, unusual coincidences often prompt questions about whether the data reflect deeper mechanisms or simply statistical outliers. At the very least, such circumstances create opportunities for unique observational campaigns. In this case, the geometry of the object's trajectory provided the perfect setup for measuring solar gravitational lensing, a test that depends critically on small angular separations and precise timing. The deflection calculation based on general relativity is itself a valuable teaching example, demonstrating how classical gravitational parameters interact with relativistic corrections and geometric distances to produce measurable physical outcomes. For students encountering relativity in an astronomy course, such as the one soon to be taught at Harvard's astronomy department, this real-world application highlights the continued relevance of Einstein's theory more than a century after its formulation. Observing a deflection angle that matches theoretical predictions would further validate the robustness of general relativity in yet another astrophysical context, this time involving an interstellar object rather than a star or galaxy. Conversely, if the observed value deviated significantly from predictions once all non-gravitational accelerations were accounted for, it could hint at unmodeled physical processes or provide motivation for refinement of the object's physical characterization. Meanwhile, the ALMA reported deviation in the object's position strongly indicates that 3I/Atlas is subject to forces beyond simple Keplerian dynamics. Non-gravitational accelerations are not uncommon in comets, which can experience jets of gas or dust that alter their trajectories. However, 3I/Atlas is not a conventional comet, and its anomalous characteristics, including brightness behavior, color, and pre-perihelion acceleration, suggest that the mechanisms driving its motion may not align neatly with known cometary physics. The small but detectable effect of gravitational lensing becomes, in this context, an additional component that must be carefully extracted from the total deviation. This makes the analysis more complex, but also more intriguing. Extracting such a tiny signature from a motion dominated by larger forces is a challenging, but scientifically rewarding endeavor. One of the most captivating aspects of the entire episode is the interplay between classical orbital mechanics, relativistic physics, and unexpected astrophysical behavior. Each new dataset, whether from ALMA, STEREO, SOHO, or GOES 19, adds another layer to the puzzle, forcing astronomers to re-evaluate models, examine assumptions, and consider new mechanisms. For interstellar objects like 3I/Atlas, which arrive unpredictably from beyond the solar system, every observation is precious. They may carry chemical, structural, or dynamical information that can shed light on physical processes occurring in distant star systems or interstellar space. Anomalies, whether in brightness, trajectory, or spectral signature, may provide clues to environments or formation histories that differ drastically from anything within our own planetary system. In summary, the passage of 3I/Atlas through the inner solar system in late 2025 provided an unusually rich set of observational opportunities due to its unique orbital timing and its unexpected physical behavior near perihelion. The gravitational lensing effect caused by the Sun, predicted to produce a small but measurable deflection in the object's apparent position, is a particularly fascinating aspect, both scientifically and pedagogically. Coupled with non-gravitational accelerations detected by ALMA and the dramatic brightening and unusual coloring observed by solar spacecraft, these features collectively contribute to a growing list of anomalies. Whether these anomalies ultimately reveal new physics, unusual material properties, or simply uncommon configurations remains to be seen, but the data collected offer a remarkable chance to deepen our understanding of interstellar visitors and the fundamental laws that govern their motion.